Okay, good afternoon. So to this last lecture, that's lecture number 11, and it will only take like an hour or so for today. As usual, I would like to start with a short summary of what we have done so far and where we are in the course. And well, we're dealing with stability and transition of shear flows, and we have always been interested in this diagram here, where the main aspect was that we want to look at the flow as a function of Reynolds number. So the Reynolds number takes the role of a bifurcation parameter. The Reynolds number is that parameter that decides whether a flow will be laminar or turbulent. And of course, the reason why this is called the Reynolds number and why this is important is, of course, because the Reynolds number encodes the effect of viscosity. Low Reynolds number means a lot of viscosity, and high Reynolds number means lower viscosity compared to the convective or advective forces. So an airplane at high speeds will always be at high Reynolds numbers. Small microfluidic devices will most probably be at low Reynolds numbers. And of course, this all goes back to Osborne Reynolds, who was the first person that studied this flow, this parameter, when he looked at pipe flow and looked at what non-dimensional parameter the pipe flow became turbulent. And then he came up with the Reynolds number, or actually he came up with the inverse of the Reynolds number, and then it was later called the Reynolds number in his honor. But so the basic idea really is that we have this ray here on which with the Reynolds number, and we have identified two important Reynolds numbers. One is ray G, which separates the part where everything is just decaying. That's kind of this region where we have the energy of the flow decaying, no matter how big or how the disturbances look like. And then we have ray C, which is the critical Reynolds number, which is obtained by looking at the eigenvalues. So the linearized version of the equations is considered to find out at what Reynolds number you get exponential growth of your instabilities. So that's ray G and ray C. Then we have also looked at one limit here, which is the Reynolds number going to infinity. And that was actually then the topic of the Rayleigh inflection point theorem. That's what we discussed last time. The idea was to look at certain velocity profiles, and just from the shape of those profiles, determine whether or not one can get a inviscid instability, so an instability that does not depend on the presence of viscosity. And there's two important theorems here. That is the Rayleigh inflection point theorem, and also Fjordhoft theorem, which is from 1950. The Rayleigh inflection point criterion essentially says if you have a base flow, so if you have a laminar flow where you have an inflection point, then the profile may be unstable. So it's a necessary but not sufficient condition. Of course, an inflection point essentially means that the second derivative needs to be zero somewhere, and the second derivative being zero means that the curvature of the profile somewhere needs to be zero. So that was the Rayleigh inflection point theorem from 1880. That was kind of the first time that somebody, in this case Rayleigh, was actually looking at velocity profiles to determine whether or not there could actually be something unstable. Fjordhoft was later on improving on the Rayleigh criterion by giving yet another restriction of when a profile could be unstable, and he said that this inflection point that you have actually needs to also coincide with a vorticity maximum. So there needs to be a peak in vorticity at that point, not a minimum, but a maximum. It's still only a necessary condition, but still it's more restrictive. So you can much easier determine whether or not the criterion would actually be unstable. And we looked last time also at a number of profiles. So for instance, we have here kind of a channel flow profile where we see that actually the point where we have the inflection point does not correspond to a vorticity maximum. So this would be a stable profile in the limit of infinite Reynolds number. And then we have this, the second type of profile here, where we have in this point an inflection point, but this would correspond to a vorticity minimum. So that would also not be unstable. And then the last profile, we have again an inflection point, and in this case it would actually correspond to a vorticity maximum, and that is now a profile which is potentially unstable both from a Rayleigh point of view but also from a Fjørtoft point of view. And this last point, that corresponds to the well-known shear layer instability. Shear layer in the sense that you have a region between two flows where they shear with each other, and that's exactly what happens, for instance, in a mixing layer. So when you have kind of a splitter plate, you have a high-speed fluid on top, a lower speed fluid on the bottom, and then you have this shear region. Then you would get exactly this type of profile, which is then invisibly unstable. You would also get it on the sides of a jet, for instance. That's exactly the shape that you would get there. And that also explains why these types of profiles are actually quite unstable, and we see this type of instability, which has been termed Kelvin-Helmholtz instability, quite often in our surroundings. Yeah, so these were this was the Reynolds infinity excursion. Then what we have talked about quite a bit was this region where the eigenvalues are larger than 0. This is kind of the, with the Sommerfeld equations, and we looked at the so-called TS waves, or Tolmin-Schlichting waves. And then this region here we have considered while looking at the this one. We have looked at by considering the Reynolds OR equation. What is still a little bit open is this blue region in the middle. We just started last time talking about that, but that's kind of what is a little bit curious, and it was kind of not really understood up to maybe 30 years ago. The reason for that is that this blue region here in the middle does not always occur. Not for all flow cases. You actually have separate ray G and ray C. And as kind of by chance, the first flow case where stability theory has been applied was the Rayleigh-Benard flow, and it was kind of done by Lord Rayleigh in 1916, if I'm not incorrect. And actually for the Rayleigh-Benard flow, it turned out that ray G and ray C were very, very similar. So if I'm just adding this here, maybe. So Rayleigh-Benard, it turned out that the critical Rayleigh number was 1708. And actually it turned out that this was really ray G and ray C at the same position. So everybody was very happy and thought, okay, now we have understood everything. But then it turned out that when people started to look at channel flow later on, so really a shear layer, shear flow, well, they then saw that in channel ray, the critical Reynolds number was this 5772, which we have calculated ourselves, and ray G, so the energy stability, was somewhere at around 50. So you had this huge gap between ray C and ray G. So the blue region here was actually very extended. So we needed to, or one needs to understand what is actually happening there, and in particular, what type of growth or what type of instabilities that one could get there. And this is now what we started to look at a little bit last time, and that topic is called transient growth or non-modal stability. Because the reason why we called it non-modal is, because modal stability would be the growth, the exponential growth of normal modes. So you would pick one eigenvalue, which is in the positive imaginary half plane. So that means they have a positive growth rate. And of course, with a positive growth rate, you will have exponential growth in time, in this case, if you look at the temporal problem. And that is what we would call modal growth. Because it is really based on the individual growth of normal modes, like Fourier decomposition. But now it turns out that there is also something that we call non-modal growth, so growth that is not related to the growth of individual eigenvalues. And exactly that's what we would like to look at. Now, what we have done so far, or last time, was that we started to look at a kind of a shorthand for our linearized problem. It's exactly the same dynamical system that we have looked at earlier. dq dt is L times Q. Q is the quantity, could be the velocity or something, and L is the kind of the linearized operator or the Jacobian of the nonlinear system. The way that we now would like to look at this is to not go via a normal mode approach, but we will directly just go as an input or so-called input-output formulation. Input-output formulation means that we have a certain input, which is our initial condition, Q0, let's say, and then we have a certain output, which is Q at a certain time. Maybe I can write it in this way. So this is Q as a function of time. And then we have something that takes the form of a transfer function that kind of takes our input and gives the output. And in accordance to how one would solve such a problem, we can just, in accordance to how we solve a linear partial differential, linear, not partial anymore, but an ordinary differential equation as the one here, the solution would just be, well, Q0, the initial condition, times the e to the power of t times L. And now, in this case, because L is a matrix, we call this function to be a matrix exponential, which is a valid mathematical function, which is also implemented in MATLAB, for instance. The definition of a matrix exponential is just a Taylor series expansion that you also have for a normal exponential. Now, the question that we were asking then, and that was exactly what we did at the end of last time, the question that we were asking ourselves is, what is the maximum energy growth that we could actually get from looking at this matrix exponential? So we define an energy amplification, G of t, which is the maximum over all Q0, so over all initial conditions of this functional here, which is Q of t, which is the amplitude at a certain time divided by its initial condition. It's linear, so that means the scaling doesn't matter, so we can scale out the amplitude of Q0. So this here would be this G of t, that's the amplification that we could get, and this is, if we're interested in growing solutions, is what we would like to maximize or understand better. So let's maybe directly continue with this. So let me just copy this and continue here. So this is the quantity, or this is the functional that we're interested in, or that we would like to look at. Something is weird here. My pen doesn't work anymore. Don't know what the problem is. Okay, now it works. Okay, so we would like to look at this this function here, and of course now we can continue. So this is the maximum over Q0, and T is that is just this matrix exponential that we have written before. So it's x of T times L, with L being the matrix, times Q0 squared divided by the norm of Q0. And just to introduce another kind of shorthand, I can now say that this x of T times L, this could be an operator which I can call capital Q. So that's exactly this, this transfer function. So Q applied on Q0 squared divided by the norm of Q0. So what it means at the end is we would like to know what is this Q operator, this transfer function actually doing. And in fact, if you now just kind of look at this, it is quite clear that we can define a new matrix norm, which essentially says that this G of T would be the norm of exactly this x of T times L to the power of 2, or that would just be the norm of this Q. So that means we can now define the norm of this matrix L as being this or the norm of this of the whole exponent as being G of T. And this one would fulfill all the properties of a norm in terms of linearity and so on. So that means if we want to ask the question of what type of growth we have, we need to look at this matrix exponential or this Q factor in order to determine whether something is growing. Okay, now let's look at this a little bit more. So it's G of T that we would like to understand, or x of T times L, and the normal. Now, essentially, this is the L is the linearized operator, the Jacobian, which we have already looked at earlier when talking about the eigenvalues. So we actually know something about L. We already know the eigenvalues of this operator L. And keep in mind, the L is the Jacobian, so that would be for instance, the Orr-Sommerfeld operator. That would be the L here. So if we now know the eigenvalues and eigenvectors, well, we can decompose this L into S times lambda times S minus 1, where in this decomposition, the S here would be the eigenvectors. And the lambda here, that would be a diagonal matrix with all the eigenvalues on the diagonal. So that would be a matrix that looks like this: lambda 1, lambda 2, lambda 3, and so on. And the rest would all be zeros. And of course, S minus 1 would be the inverse of the eigenvector matrix. So this is nothing else than the decomposition into the eigenvalues. So all the eigenvalues and eigenvectors that we have calculated before in order to determine the spectrum and the stability, we already know, and we can use to decompose this L. But now the question is, does this help in any way when we're interested in G of T? So what we can do is we can just plug in this eigenvalue decomposition directly into the matrix exponential. So what we have then is exp of T times, now comes the L, which is S times lambda times s minus 1 squared. I mean, so far we have not done anything, but the interesting thing now becomes, if you recall the definition of the matrix exponential. So if you now go up, and I hope it's written here. So here is the definition of the matrix exponential. And that means, or what you see here is that at the end, it will be, the matrix exponential is an infinite sum of the matrix up to a power of k. So I mean, it's a repeated sum. So that means actually that we can rewrite this one here as the following: the norm of s times the exponential of t times lambda times s to the minus 1, the power of 2. So we can take out the s and the s minus 1 out of the brackets. Well, why can we do that? We can do that exactly because of this infinite sum here, because each x to the k will be, s times the xt to the lambda times s minus 1. And then if it's multiple ones, there will be another s times xt to the lambda times s minus 1. So all the internal s times s to the minus 1, they can be connected and will give the identity. And in the end, it's just the first s and the last s to the minus 1 left, which we can then take out. So that means this last equal sign, this one here, actually comes from the definition of the matrix exponential. So that we can write it in this way. And now, this has actually become very interesting, because this guy here, the exp of t to the lambda, this is now much simpler, because this is the matrix exponential of a diagonal matrix only. And of a diagonal matrix, well, we know what the exponential will be. It is just e to the t lambda 1, e to the t lambda 2, and so on the diagonal, and it will be zeros everywhere else. And of course, this now is exactly what we have done all along. This is just the traditional stability analysis. So the modal stability analysis, where we look at growth of individual eigenmodes. But what the difference now is that we have also this s and the s minus 1 before and after this this matrix here, this diagonal matrix. So I guess now the question is, under what circumstances do we have an additional growth even if the eigenvalues are lower than 0? So I guess the first conclusion from this is that the growth g of t is the same as just the norm of x of t times lambda, so the eigenvalues. This is only the case if, well, essentially it means that s and s minus 1 need to be a bit special. They need to be such that they would not contribute to the norm. And what does not contribute to a norm? Well, it is only then when s and s minus 1 are pure rotations. They don't change anything. There's no stretching or anything else involved. So if they're pure rotations. So that means g of t is this only if s and s minus 1 if s and s minus 1 are what is called unitary. That means they have the eigenvalues are the eigenvectors are orthogonal to each other, so therefore it's only a rotation without the deformation, and the amplitudes are kind of 1. So the unitary, i.e. the eigenvectors are orthogonal to each other. Or the other word here is also that the eigenvectors are normal to each other. And actually it turns out that this was exactly the case in Rayleigh-Bénard convection. Rayleigh-Bénard convection. So if you write down the eigenvalues that you get and the eigenvectors for Rayleigh-Bénard convection, you will see that you get a set of normal or orthogonal eigenvectors of your Jacobian. And of course, that means that your growth here, so the G of t, can be expressed entirely by just looking at the middle part here, because S and S minus 1 do not contribute to the norm. So everything is just determined by the eigenvalues. That was the reason why Ray G and Ray C is exactly at the same point for Rayleigh-Bénard. For all other situations, so if S and S minus 1 are not orthogonal to each other, then the S and the S minus 1 in this norm will actually contribute to it. They may increase or decrease the growth given by the eigenvalues. So otherwise, S and S minus 1, they contribute to the norm, and as a consequence of that, what we will get is a transient amplification is possible. Transient amplification despite all eigenvalues being, or all eigenvalues, now it should be, say, lambda I, so the imaginary part being negative. So how can we now physically understand what I mean with this? I mean, mathematically, I think it's pretty clear. We see now that if S and S minus 1 are just pure rotations, nothing really happens to the norm. And if they're not orthogonal, so there's also stretching involved or a change of direction involved, then some transient growth may be possible. But if I would like to draw that or make a sketch that makes this clear, I think that would be quite useful. Let's try to do that. First, I illustrate the normal orthogonal way of doing things. So let's have here two directions. I can say this is a direction in eigenvector number 1, and this is the direction of eigenvector number 2. And they are orthogonal to each other. That would be an orthogonal V1 and V2, which at the end of the day means that V1 times V2 is 0. So they're orthogonal to each other. Okay, so let's assume I start here and here with, this is at time 0. So I have a projection of my initial condition onto V1 and V2 like this. So that means that kind of my vector at the time 0 would look like this. And now I'm assuming that all the eigenvalues are negative. So that means that the projection into the direction of V1 and into the direction of V2 decays over time. So that means that maybe, this one, maybe V1 decays a little bit slower. So these are maybe the kind of the times that it will go down. And V2 decays a little bit faster. So maybe first time it's here, and then here, and then here, and then here. Something like that. So that means that the first time, taking red maybe, would kind of be here, this point, and the next time would be like this, here, then maybe here, and then here. So that means somehow the amplitude has, or the vector kind of looks like this. And of course, what you can see from this is that the length of the vector, which then corresponds to the norm, is always decaying. So the norm gets smaller and smaller. And this is, for the orthogonal case, when the two eigenvectors are orthogonal, then we can clearly see that the sum is actually decaying. And I guess this is not very surprising. This is what you would expect from such a system to do. But I think more interesting now is to consider what happens if I have two eigenvectors that they're actually not orthogonal to each other. But this is a little bit difficult to draw, and I hope I do it well. So I have, let's say, one eigenvector which is like this, and I have another one which is, let's do it a little bit longer. So this would be V1. So these are clearly not orthogonal to each other because they have a larger angle than 90 degrees between each other. Now we do the same game. We say that the initial condition has a projection in onto these two eigenvectors, which looks like this. And of course, this would mean then that the original vector at time 0 would look like this. Now we do the same thing. We say that V1 is decaying, but not so fast, but it's decaying, something like that. And V2 is also decaying, but it's actually decaying much faster. So maybe like this. And now the question is, can we now? So how does the length of this original vector depend or look like as a function of time? So we try to draw that like this maybe for the first time. We have something like this, and we have something like this. It actually turns out that if I had now drawn this properly, that there may be, okay, maybe I should have maybe drawn the angles a little bit. Let me try once more. I'm sorry, this was not very good. If I just do it a little bit more acute here, so the same thing. We have here one that is decaying very slowly. So the first one would now be no, not like this. Sorry. So this would be the initial condition. This looks terrible. So this would be the initial condition at time 0, and then because this one is decaying very fast, it would then be something like that, something like that. So what would actually happen is that you would get a transient amplification of this point here, that it would actually go, it would be longer for a certain time, and then only after some time, when the first or the second eigenvector in this, the projection, the second eigenvector would be very, very small, it would just follow with the decay of the first eigenvector. So this situation here would be the non-orthogonal situation, where we actually have a transient amplification, just because you will have initially, or you may have initially, a partial cancellation because of the non-orthogonal angles. At very long times, you would again just end up with the most dominant eigenvalue. So you will get back into the decay that you would get from this most dominant eigenvalue. But transiently, you would actually get amplification. So now the question is, now we see that if we have orthogonal eigenvalues, we have growth. We have no growth. But if we have non-orthogonal ones, we may have the potential for this transient growth. Now, I guess the important question is there a way of being able to predict whether or not there will be transient growth? And actually there is. And we can just look at what is called the condition number of our eigenvectors. So the condition number of the matrix S, which is the matrix of our eigenvectors. So the definition here, that's kappa of S, is simply the norm of S squared times the norm of S minus 1 squared. And of course, if this is orthogonal, then S and S minus 1 cancel each other. So that means kappa over S is simply 1 or unity. And that means then we're in the situation where we have no transient growth. Right? I mean, this you can directly also see from our original equation. So if S and S minus 1 are orthogonal to each other, they will really not contribute to this norm. But as soon as the kappa of S, so the condition number, is larger than 1, so that means when we're non-orthogonal, then kappa of S is larger than 1. And of course, the more it is larger than 1, so that the more non-normality you have, the more transient growth you have. So that's why I say kappa of S is much larger than 1, then we will probably get transient amplification. Now, this all perhaps looks or sounds quite theoretical, but I would like to give you a clear example of how this is actually for channel flow, so for Poisson flow. So if we again draw our ray of the Reynolds number, we have here the two critical Reynolds numbers. So this one is ray G, which is around 50. Then we have ray C, which is 5772. And then we have the region where we have no growth. We have the region with unstable eigenvalues. And we have the region in between, which we'll call the transient region. Well, how does this now really look like? So if I wanted to plot G of t for these different regions, well, if I do it here, so this is G of t as a function of t, and I start somewhere, time being 0, it will just go down. And whatever I do, whatever initial condition I have, it will just go down. But there's nothing very interesting. Down here, when I have unstable eigenvalues, again, t and G of t, well, here it means that when I start here, for instance, initially, things may happen, but at some point, I will actually end up with the growth rate that corresponds to my most unstable eigenvalue. So my G of t will actually follow e to the lambda 1 times t. Lambda 1 being the eigenvalue with the highest imaginary part. And of course, in this case, we know it's larger than 0 because otherwise we would not be in the region of Reynolds being larger than Reynolds C. So that means eventually we will end up with exponential growth proportional to e to the lambda times t. Now in this transient growth region, that's the new region now, I also like to plot this. Well, it kind of means that if we start here, for instance, we may have, and that's now depending on the initial condition, but if you just plot the envelope, which is the g of t, it would maybe look like this. It may transiently grow. Notice when these eigenvectors kind of overlap or cancel each other in this very specific way, but then they will reach a maximum. But then at some point, the transient growth is over, and it will actually start to decay exponentially. And of course, because we know that all the eigenvalues are actually lower than 0, this line would again be proportional to e to the lambda 1 times t, but just with the difference to here, that here the growth rate is lower than 0. But we have this region here where we have transient growth, and that's exactly due to the reasons that I tried to sketch here. When you have this overlap, or that the partial cancellation of the eigendirections, which then may lead to this transient amplification. And I guess here it's really important to understand that any specific initial condition may have a different kind of a different behavior. Maybe this one would look like this, or one initial condition, but then you may have another one that is looking like this, like this. So that means this green curve, so the g of t, which is the maximum over all initial conditions, that is kind of the envelope of individual growth curves that you will get here. So this means this is now what is called transient growth. Okay, now to conclude this topic, I have prepared one poll, which is maybe a little bit simple now, but I still would like to look at to ask you that. So I guess this is in some way the summary of this chapter for today. So the question is, can you get growth if all the eigenvalues are lower than 0 in the imaginary part? So if all the imaginary parts are lower than 0. This is a multiple choice question, so it's not just one answer that is correct. So can you get growth if all eigenvalues are lower than 0? The different answers are no way, only for a short time, always, or only if you excite exactly one eigenvalue, or you need at least 2 eigenvalues for having this growth. And I guess if you can answer this question and you understand all the answers, then you have understood what is meant with transient growth. So therefore, I think it's good if you go through that, and then we very briefly go through all the answers to make sure that it's all clear. So again, the question is, can you get growth if all eigenvalues, or the imaginary part of all eigenvalues, is lower than 0? Can you get growth? No, only for a short time. Yes, only if exactly one eigenvalue is excited, or you need at least 2 eigenvalues for that. Okay. Let's see what the answers are, or what the possibilities are. So again, what I'm asking here is, I'm having the situation that all the eigenvalues are lower than 0. So that means, if I go back to here, when I wrote my amplification as the norm of S the eigenvectors times x t times lambda, so that's the diagonal matrix, times s to the minus 1. So if this is my growth, I'm in a situation that lambda 1 and lambda 2 are all lower than 0. So that means exp of t times lambda is a matrix where each diagonal entry is decaying over time. So that's kind of the starting point. Now the question is, can I get growth of g of t even if the matrix entries decay? And I guess no way is, of course, a wrong answer, because obviously we can, because that's exactly what we're talking about here. So yes, it is possible. Is it always possible? That's the third answer. No, you need to have a special condition to be fulfilled. Namely, the condition you need to have is that s and s minus 1 are not allowed to be orthogonal. Because as soon as they are orthogonal, then s and s minus 1 do not contribute to the norm, and the norm of g of t, which is the norm of the matrix exponential, will just be exactly the norm of this e to the t times lambda, which is decay. So that means, no, it's not always possible. It's only if s, the eigenvectors, are non-normal, non-orthogonal. Now, the second answer, well, only for a short time. Yes, exactly. It's only possible for a short time, because for longer times, it is still the most unstable eigenvalue that will dominate. So for a long time, you will not have growth anymore, and it will be dominated by the largest eigenvalue, which in this case is actually stable. So that means it will decay eventually. So that means the correct answer is only for a short time. So that's why we call it transient growth. Now the last two options are, well, is it possible to get growth only if you excite exactly one eigenvalue? No. If you only excite one eigenvalue, I mean, go back to this plot. If you were only to excite, or my disturbance has only a component in the V1 direction, for instance, well, then of course, it will just decay, because V1, the projection on V1 is decaying. There's a negative eigenvalue, lambda 1 here associated to V1. So that means if you only excite one eigenvalue, or one eigendirection, or eigenvector, I should say, perhaps, then it will decay. The trick comes when you have the superposition in the sum of at least two eigenvectors. I mean, this sketch here, which is not a particularly good sketch, but in this sketch it is with two. But of course, you can imagine if you have three and more eigenvectors, it becomes even more intricate to describe. But you need to have at least two eigenvectors that are superposing each other in order to have this transient growth. So that means the correct answers for this question would be, well, only for a short time, and you need at least two eigenvalues to be, contributing to this. Okay, so this was my first poll question. My second poll question, and regarding time, if that's okay, I would continue because I'm finished in like 10 minutes, or actually in 5 minutes, perhaps. So therefore, I think it's better to continue and then just finish the course for today. My second poll question that I would like to ask you today is the following. To find it. So my question would be, when you now think physically, when or under what circumstances do you actually see this transient growth? And now the question comes up here. So physically speaking, when is this transient growth, so this transient amplification of, in principle, stable eigenvalues, when is this important or when is this relevant? And I'm now using the terms transient growth and bypass transition as synonyms. Bypass transition, as I mentioned earlier, is just a case. It essentially means when I'm not relying on exponential growth. So everything that is not growth of TS waves is kind of bypass transition, if you wish. So when is this relevant, transient growth? All the time? Nowhere? Or rather in what we would call high disturbance environments? So that may be, turbo machinery cases. So when you have kind of a lot of free stream turbulence. Or could it be in low disturbance environments? So for instance, the calm flow on airplane wings. When is bypass transition or transient growth relevant? And when is perhaps the more modal approach, like TS waves and so on, more relevant? What do you think? I see that there's some answers coming in. I guess everybody agrees that it's neither everywhere nor nowhere, what I see from here. But it seems it's a bit shared opinions whether this is high disturbance or low disturbance. It's exactly 50-50. Let's say either or. Well, so I would say classical modal transition or instability, that is relevant when you have low disturbance environments. And of course, this has to do with the fact that if you have a low disturbance, so essentially zero disturbances, you would actually rely on the exponential, or you would see the exponential growth of one individual mode, let's say the TS wave. You would see that and you could follow that, and you could also, in case, control it. If, on the other hand, so if you have bypass transition, that would then be in the case when you have high disturbance levels. So that means when you have a lot of disturbances, free stream turbulence that penetrate into the boundary layer, when you have a lot of different frequencies acting, which also means that a lot of different frequencies are excited in the boundary layer. So your disturbance has projections on all kinds of eigenvectors. They all kind of grow or decay depending on the eigenvalues at the same time. So that means that there is actually potential for this superposition of different eigenvectors, or that the disturbance actually has projection on different eigenvectors. And this is mainly the case if you have a lot of disturbances. So that means what I showed you here, this transient growth, that is mainly relevant if you're having high levels of disturbance. So free stream turbulence, for instance. Turbo machinery I was mentioning, there's where everything is kind of vibrating and so on. But it's not relevant on airplanes. If you have an airplane at cruising altitude, it's mainly modal instabilities that happen. It could be, TS waves, it could be cross-flow instabilities, but all kind of dominated by single eigenvalues, not the superposition. And that's maybe also important to remember when talking about transition. For this, I just wanted to show you again 2 slides that I've shown you before. That's again my slides on transition. But this image here is the one that I typically use to explain classical transition, so the modal instability. So that means in this case, when I have low amplitudes of free stream turbulence, I can see this exponential growth of the TS wave, these guys here. And you see branch 1, when it first starts to amplify, you see that the amplitude is increasing, and then you get secondary instability of this, and then break down to turbulence using these, or via these lambda vortices. Same time when you have high levels of free stream turbulence, so you have here a lot of disturbances further away from the boundary layer. What you then excite inside the boundary layer are these streaks. And actually, these are not, as we now know, these are not TS waves. I mean, they look different. They have a different orientation. And actually, these streaks, they all grow transiently. They only grow because of the interaction of different eigenmodes, but they are not actual eigenmodes inside the boundary layer. No, the eigenmodes, they are TS waves, spanwise waves. These are streamwise, vortices essentially. And then these streaks, they grow transiently, and then at some point they will break down to turbulence and then create this fully turbulent flow. So that means that if you have high levels of free stream turbulence, then it's really this slow exponential growth of TS waves is taken over or bypassed by the transient growth, which may actually be much faster. It's not exponential, so the overlap is not exponential, but rather a linear growth that you get. Okay. So I guess with this, I have now shown you everything I would like to show you for this transition or stability and transition part of the course. And I guess with this, we can really conclude the topics that are also relevant for, well, both for the course, but also for the exam. So with this, I would also like to stop the recording, unless there is any more questions that you may have for this topic. So if you have any questions, you can pose it now. Okay, in this case, I will